All right, today we're jumping into something, well, pretty radical. The idea that one single geometric law could connect the dots between the inside of an atom and the biggest mystery in the cosmos, dark matter. So, let's see if the evidence actually stacks up. So, let me start by asking you this. You know how in science we always have these tiny little errors in our measurements? We usually just call it noise and kind of brush it aside. But, what if it's not noise at all? What if it's not random? What if it's actually a predictable feature of reality, a hidden message?
Okay, here's our game plan. We'll kick things off with the projection law itself. Then we're going to put it to the test, first inside the atomic nucleus, and then we'll scale it all the way up to see if it can really explain something as huge as dark matter.
All right, first up, the projection law. At its core, this whole idea hinges on a concept called the projection law. The best way to think about it? Imagine our view of reality is kind of warped, like we're looking through a funhouse mirror.
So check out this formula. What's basically saying is that the value we measure, let's call it O, isn't the real true value, which is O star. Nope, what we see is a projection, and that projection is shifted. And the key thing is, it's not a random shift, it's a predictable one. And it's all based on the scale distance between us, the observer, and the thing we're looking at. It completely flips the script on what we call error.
And here's the real kicker. That distortion, that deviation, it's not random. It's systematic. The formula there for dm, the scale distance, is what it all hinges on. The bigger the difference in scale, think about a person looking at a single atom, the bigger the predictable distortion gets. It's just like that funhouse mirror. The thing you're looking at is perfectly normal, but your view of it is warped in a way you can actually calculate. Okay, so how do we even begin to test an idea like this? Well, let's take it and apply it to a real-world puzzle. Something that's been a tough nut for physicists to crack for a long time, the stability of atomic nuclei.
So this framework predicts something really elegant. It says that deep down, at an intrinsic level, the most stable energy setups in a nucleus should follow this super simple rhythmic pattern. See these numbers? 2.5, 5.5, 8.5? They're like perfect steps on a ladder. The problem? Well, this clean, perfect pattern isn't quite what we actually measure in the lab.
And that right there, that's our first big test. If the theory's pattern is so clean, then why don't our measurements match it perfectly?
Okay, so look at this. On the left, you've got the clean, simple prediction from the theory. And on the right, that's what decades of real-world nuclear experiments have actually measured. They're close, but not quite the same. And the claim is that the projection law is the missing link. That difference isn't a mistake. It's a predictable effect of our point of view.
The difference, it's all about the distance, or more accurately, the scale distance. So let's actually do the math. The theory's argument is that this little mismatch only exists because we're huge and we're looking at something incredibly tiny.
So here's how the calculation works. First, you take our scale, the observer's scale, which the framework defines at this m equals 144,000. Then you take the target, the nucleus, which is at the base scale of 144. You find the scale distance between them, that dm value, and you plug that right back into the projection law. In theory, this should spit out the exact shift we see in the data.
And bam, look at that. When you run the numbers, the perfect intrinsic value of 8.5 MeV gets transformed into a projected value of 8.3 MeV. And that is a dead-on match for what we actually observe. It's pretty wild. What used to look like a messy experimental result is now being presented as stone-cold proof that this projection effect is real.
Okay, that's impressive. Explaining data we already have is cool. But for a theory to be really solid, it has to do more. It has to stick its neck out and make a new prediction, something we can go out and test, something that could actually prove the theory wrong.
And that's exactly what this framework does. It just takes that same simple geometric pattern one step further, applies the exact same projection calculation, and makes a really bold claim about the next big stability gap, one that we haven't even found yet.
And there it is, 14.0 MeV, give or take. This is basically throwing down the gauntlet to experimental physicists. The prediction is clear. Go look for the next nuclear magic number right around here. If they find it, wow, that's some serious evidence. But if it's not there, well, that's a huge problem for this model. And that's exactly how science is supposed to work.
All right, now let's pivot. We're going from the incredibly small to the mind-bogglingly big. Can the exact same law that we just used for an atomic nucleus, can it really explain one of the biggest puzzles in all of cosmology?
So you know about dark matter, right? The standard view is that it's some mysterious, exotic particle that makes up most of the stuff in the universe. But this UFRF idea, it's completely different. It says dark matter isn't a thing. It's not a particle. It's just that same projection effect we saw in the nucleus, but now it's happening on the scale of galaxies. It's not stuff. It's a shadow.
Now, a claim that bold, saying dark matter isn't real, that needs some extraordinary evidence. So the framework points to a very specific place to look for that evidence, in the way we measure galaxy clusters.
It turns out, for a while now, astronomers have had this weird little puzzle. When they measure the mass of galaxy clusters using two different methods, the answers don't quite match up. There's this consistent 4% gap. Most would say, it's a measurement error, or maybe some extra dark matter we missed. But this framework says, no, that 4% isn't an error, it's the signature, it's the projection effect.
So they take the projection law and they apply it to the immense scale distance between us and these galaxy clusters. And it spits out a very, very specific prediction. It says the ratio between those two mass measurements should be precisely 0.961.
So what does the actual data say? Well, observations from a major galaxy cluster survey called LOCUS show the average ratio is 0.962. Come on, that's an unbelievably close match. That little 4% discrepancy that was a puzzle, now it's being presented as maybe the strongest confirmation of the whole idea.
And that's really the main thing to wrap your head around here. The claim is that a single, incredibly simple rule about perspective connects the tiny energy gaps inside an atom to the apparent missing mass of entire clusters of galaxies. And, in both cases, it seems to nail the numbers.
Which, of course, leaves us with a pretty mind-bending question to chew on. If our most precise measurements of reality are really just shadows, predictable, geometric shadows, then it makes you wonder, what's the real object that's casting them?